Alright, so I think this is recording now. Let's take a look at problem number 2. Parts A, B, and C are pretty easy because we're just plugging in numbers. So you've probably seen this in Algebra 2, that they simply use a notation f of g of 3. So I need to replace this g of 3 with a number. How am I going to do that? Well, I'm going to apply the function g to this number 3. G always takes 1/3 of the input that you give it and then adds 2. Well, what we're giving it, the input is 3. I don't know why I highlighted the whole thing. I wanted to just highlight the 3, but 1/3 of 3 is 1, and 1 plus 2 is 3. So now I'm going to plug 3 into the number into the function f. F always takes the input no matter what it is, multiplies it by 3, and then subtracts 6. This time our input is 3. 9 minus 6 is 3. So this function composition evaluated at 3 just also happens to equal 3. Here's our answer for part A. In part B, we want to take this -9 and first plug it into the function f, get that output, and then plug that into the function g. When we plug in -9 into f, what do we get? Well, f always creates a subtraction problem. 3 times the input minus 6. This time the input is -9. 3 times -9 is -27. And -27 minus 6, I think, is -33. It's getting late, and I'm not sure exactly what it is, but hey, I think I'm going to go with -33. G always creates an addition problem. It takes 1/3 of the input, whatever that input is, and then adds 2. This time our input is -33. 1/3 of -33 is -11. And -11 plus 2 is a -9. So this G composed with F has an input of -9, and it also has an output of -9. So later we're going to recognize that these two functions undo each other. That when we plugged -9 into f, f did its magic and got -33, well then it undid that and went back to -9. These functions are undoing each other, and they are called inverse functions. When we find the expressions for f composed to g and g composed with f in parts D and E, we're going to see that it's going to reduce to x, I'll bet you anything. Anyway, let's find out. So maybe I'm getting ahead of myself. This is the answer for part B. Let's take a look at part C. Now in part C, we're not using G at all. It's wanting to plug 0 into the function f, get an output, and then plug that output into f again. So what does f do to the input? F always creates a subtraction problem. 3 times the input minus 6. This time the input is 0. So 3 times 0 is 0. 0 minus 6 is a -6. So again, what does f do to the input? It creates a subtraction problem. 3 times the input minus 6. This time the input is -6. -18 minus 6 is -24. F composed with f, when evaluated at 0, is equal to -24. There's our final answer for part C. Now, in part D, they're going to ask us to find an expression for fog, I think. Yeah. Alright, so f of, we're taking the function g and we're plugging it into the function f. What is the function g? Well, g is simply 1/3 of x plus 2. That's what this g of x is equal to. This equal sign is saying that although these two look different, that this g of x is the same number, it's the same thing as this guy, 1/3 x plus 2. Alright, so let's not write in a highlighter. What does f do to the input? F always creates a subtraction problem. No matter what we give it, it's going to multiply it by 3 and then subtract 6. This time, we're giving it 1/3 x plus 2. So if we distribute the 3, 1/3 of 3 is 1, and 1 times x is just x. 3 times 2 is positive 6. Negative 6 cancels each other, and hey, we just get x. So this is like the identity function, that whatever you plug in to this composition, you get the same thing as an output. That agrees with our answer in A. Our input was 3, and our output was 3. This formula is telling us that that's always going to be the case. Whatever number we put in between this parentheses right there, it's going to be the same number that came out. So we put 3, and out came a 3 in part A. So these answers are not contradicting themselves, I guess, is what I'm trying to point out. Let's not highlight that. Let's erase that. Let's highlight this, because that is my final answer for part D. Well, let's find, oh, was I supposed to find the domain for this? Did I cut off part of, I did, I accidentally cut off. Let's find the domain. Alright. Two things have to be true every time we find the domain of a composition. Our input, x, has to be in the domain of the first function. We're inputting a number into this first function, and in this case it's g. So I have to make sure that x belongs to the domain, is a member of the set that's the domain of g. The output, g of x, has to be, that now is the input for f, so it has to be in the domain for f for it to have an output, f of g of x. So this g of x has to be in the domain of f. Alright, well, when we figure out the domains of f and g, if you look up at the expressions, we don't have any square roots in either expression. We don't have any denominators. We don't have any variables in a denominator. So the domain for g is all real numbers. That means that we can give it any number we'd like. It's going to do its magic of taking 1/3 of the number and adding 2, and it's always going to produce a y value. So there are no restrictions. Any number we plug in, we'll get a number for output. Let's take that output and plug it into f. Well, f always creates a subtraction problem, and so this g of x is the domain for f is also all real numbers. So there's no restriction. The output can be any number at all, because f is not picky. F will take any number that you give it and create, it will multiply it by 3 and subtract 6. It will give you a y value. So the domain for this function composition is also all real numbers. So there's our final, well, not our first answer for part D was the expression that f composed with g of x is x. When we looked at the assembly line and looked at the two things that have to be true, x has to be in the domain of g, g of x has to be in the domain of f, hey, we concluded that the domain of this assembly line of this fog is all real numbers. Let's take a look here, and let's do the this assembly line in the reverse order. So we're going to this time plug f into g. So what is the function f? F is equivalent to 3x minus 6. Now, what does g always do to the input? It always creates an addition problem. First number is 1/3 of the input, no matter what that input is. Then it adds 2. we can find the input always between the parentheses. So that's what we replace x with, is this input, 3x minus 6. So this multiplication distributes over the subtraction. 1/3 of 3 is just 1. 1/3 of 6 is 2. X minus 2 plus 2, the 2's cancel, and we have x, just kind of like we thought we would, because we saw in part B that the number that we plugged in, we got the same number as output. Hey, that's always going to be the case. Now, it could be, I'm not saying that every time, what number did we plug in? I'm not saying just because we plugged in -9 and got an output of -9 that that's going to be true for every number. But I am saying that after I see the equation. This equation is definitely saying that when you plug in a -9, you're going to get an output of -9. All right, so this is my first answer for here. Now let's find the domain. Two things have to be true for when you're finding the domain of any function composition. If you look at the first function, the input has to be in its domain. The input has to be in the domain of f. Now, the output of f, we just call it f of x. It becomes the input for g. So whatever input that we plug into g has to be in the domain of f of x, has to be in the domain of g. Otherwise you would not get an output g of f of x. Well, just as before, the domain of f is all real numbers. The domain of g is all real numbers. So there's no restrictions. We can put any number we'd like into f, and whatever comes out of f, g is very agreeable. G says, hey, I'll take that number and I'll perform my 1/3 of that number plus 2, and I'll get an output. I can do that for any number you'd like all day long, forever. So the domain for this is all real numbers. The domain of this composition is all real numbers. It'll become more interesting when we have two functions that have some restrictions on there. Oh, there's a part F. I was ready to stop the video. And this part F is not using G at all. So the expression, what is it doing? It's taking f of x and plugging it into itself. F is 3x minus 6. What does f do to the input? Well, 3 times the input, no matter what it is, minus 6. This time the input is 3x minus 6. Distribute the 3, and I have 9x minus 18 minus 6. So my expression for f composed with itself is 9x minus 24, right? Now, that's my first answer. Let's find the domain of this f composed with f with itself. Two things have to be true. The input has to be in the domain of f, and the output of f has to be in the domain of f, because we're repeating the function over here. This assembly line, these two machines, these two processes are identical. This f of x has to be in the domain of f. Well, we're not going to have any problems at all here, because the domain of f was all real numbers. So we can plug any number we'd like into f. Who cares what will come out, because f will accept any number at all that we plug into it, because its domain is all real numbers. So any number we plug in goes through the first function, comes out, that output goes through the second function, and we get an output. So the domain for this f composed with f is all real numbers. The domain of f composed with f is all real numbers, meaning from negative infinity all the way to positive infinity. So that is our second answer to this part F. And I think that's now all of problem 2. Let's check. Right, let's stop the video and I'll do problem 3.